Hello and welcome to this Calculus 1 series. Today we're going to be covering infinite limits. So before we start the actual topic of infinite limits, there is just a few more limits that I have to cover. They're just kind of general rules and principles that you ought to know before you proceed. They're not really related to infinite limits, but it is useful to know them nonetheless. So these limit rules, I guess, are as follows. I also covered these in the past. So limit as x approaches 0 sine of x, that's just going to be 0. Second one, limit as x approaches 0 of cosine x equals 1. And both of these can be solved just by plugging in 0 into the respective functions. This one is again one I've covered before. Sine x over x equals 1. That's again a rule that is good to know. It's pretty useful. The next one I believe I've covered as well. Limit as x goes to 0 of 1 minus cosine x over x equals 0. And these next ones are kind of more, they're based out of logarithms and more other complex functions. The limit as x approaches a constant c of the function a to the x is just going to be a to the c. It's pretty self-explanatory. 6 is going to be limit as x approaches some constant c of log a to the ax, is again going to be log a to the c. Again, that's pretty self-explanatory. The next one is the last one, really, is involves composite functions, and it's again mostly pretty straightforward. Say you have a function f of g of x, and that's just going to be f times the limit of your inside function. Okay, so these are the some fairly important rules that you should just have memorized. And with that out of the way, there are a couple of things that I have to just go over that involve continuity of various trig functions. Okay, so how I'm going to go about doing this is I'm just going to type in the functions here, and I'll explain how the continuity is changed between them. So the first thing that you should take note is the function sine of x is going to be continuous for all real numbers, and that's pretty easily shown just in the graph itself, like this. If I can type like that, it's continuous everywhere. There's not a point where it doesn't exist. Similarly, for cosine x, it's also once again continuous everywhere. And just to show you the difference, that's the difference. If you're colorblind, I'm sorry. Then the next one is where it kind of gets interesting, is the tangent function, which is continuous everywhere for except odd multiples of pi over 2, or you can really think of that as where your cosine function equals 0. So I do tangent of x. It's right here. Yeah, you can see them right here, the infinite limits here, on every odd multiple of pi over 2. Next one is the secant function, and this is just it's continuous everywhere, but again odd multiples of pi over 2. Then another interesting one is the cotangent function, and it's continuous everywhere for except where sine of x equals 0, or really even multiples of pi. Then your cosecant function, is continuous for all real numbers except where sine of x is 0. And again, that's just even multiples of pi. Then your function a to the x, so let's say 2 to the x. As you might know, it's continuous everywhere. And the function, the log functions are all obviously continuous for all positive real numbers. I'm not really sure how to graph one of them, but that's fine. Okay, with that out of the way, we can actually start with the topic of infinite limits. And as I kind of hinted to it previously, it's really just your asymptotes. And this is a graphical example of that. And I probably sped that up in post just to make it interesting. So how you can think of these is basically something like this. Your limit as x approaches a from the right side of the function f of x, let's say this is f of x, is going to be positive infinity, and your limit as x approaches a from the left for f of x is negative infinity. And as you know, that means your actual limit doesn't exist, and that's what gives you your asymptote, in this case at x equals a. So how you'd write this is you have vertical asymptote at x equals a. It's about as simple as that. It's really just that. With that, let's solve some problems, huh? So find this limit as x approaches 3 from the left of f of x, and vice versa. I'll solve the first one, I'll let you do the next one. So we want to take a limit here, and how you do this is you first of all, you can kind of take notice that something's probably going to be happening at when x equals 3, because you're going to be dividing by 0. And what you now can do is take your limits. Let's take it from the left side first. So how you can think about this is, if you visualize a table, I'm not really going to draw one out, but let's say you take a value that is slightly less than 3. Let's say 2.9 minus 3. That's going to give you a pretty large negative number, a pretty negative number. And if you keep doing that, you're going to keep getting closer and closer to 3 at an infinitely lesser rate, I guess. You're going to keep getting closer to 3 perpetually. But your number is going to be, your y value is going to be going really, really down. So therefore, it goes to negative infinity. And similarly, it's the same logic, but for as x approaches 3 from the other side, f of x, if you do the same thing, 4 minus 3.1 minus 3, you're going to get 0.1 in the denominator. And that really means you're multiplying by 10, I believe. And that same logic applies. You're just going to get infinitely larger overall, and therefore it goes to positive infinity. This shows that they don't equal each other, and therefore you have the limit doesn't exist, obviously. But however, you have a vertical asymptote at x equals 3. And that is the primary use of infinite limits. you can use them to solve for horizontal asymptotes, but that really just means it's the same procedure, you're just getting a different number. You're basically setting your x to approach infinity from either side, and then you solve. Let's do the second one. I'll let you do this one if you're watching. So if f of x equals 4 minus 4 over x minus 3 squared. Alright, I'll give you a second. Okay, your second's up. You could have paused that, obviously. So let's do the same thing again. Limit as x approaches 3 from the left of f of x. In this case, because it's squared, even though it's negative here, it doesn't really matter anymore, so it goes to positive infinity. And then the limit as x approaches 3 from the left. Again, it's going to be obviously positive in this case. So therefore, in this case, the limit as x approaches 3 of this f of x equals infinity. It's pretty self-explanatory. If you look at the graph of this function, it's going to be like an inverse square graph, probably. And that's why you have the infinite limit that it actually goes to infinity on both sides. Alright. For these next couple of problems, how about you go and find the equations for all the asymptotes. So let's do this one. F of x equals x over 4 minus x. I will give you a second to solve this. Okay, your second is up now, and let's do this. So let's first solve for vertical asymptotes, because that's the most obvious one to solve for first. Alright, so how we can approach this is you have to first look at where your function can't really exist, and in this case it's going to be at x equals 4. So what you do is take your one-sided limits. Alright, and you're going to get negative infinity, sorry. And then as x approaches 4 from the other side of f of x, you're going to get positive infinity. And that shows that you have a vertical asymptote at x equals 4. It's pretty self-explanatory why that works, and if you graph it, it'll make more sense even. The next one is slightly less obvious, I suppose, and it's solving for the horizontal asymptotes. And while they might sound slightly more challenging to solve for, they really aren't. What you're doing is you have to now solve for the limit as x approaches positive and negative and infinity. So your setup is essentially the same, except that you're doing this now. Something like that. And there's a slight different way of solving this to make it a bit more algebraically sound. So if we're going to do it, let's do it like this. So what this really equals is this simplification or rewriting of it. It's x over negative x, 1 minus 4 over x. And when I simplify all that, it becomes this. Alright, so we can now take our limit as it goes to positive infinity. And when you do that, you'll see that this part goes to 0, so you're left with -1. And for horizontal asymptotes to exist, your both limits have to be equal to each other. Let's do the same setup for here, for the negative infinity. You can just use the same equation that we simplified and that we re-derived and simplified, I guess. And the same thing happens. It goes to 0, and you're left with -1. So therefore, you have your horizontal asymptote at y equals -1. That's that. Let's do a slightly more complex one. It is f of x equals x minus 1 over x squared minus 3x plus 2. Let me rewrite that better. Alright, so we have this, and it's basically the same process. So, your second's up, and let's do this. So, to solve for this, you really only need to care about what's happening in the denominator. The numerator doesn't matter too much. And what we can do first of all is simplify this, the denominator, and this becomes x minus 1 times x minus 2. Alright, yep. And this would suggest that we have two vertical asymptotes, and you would be correct in assuming so. So let's first confirm our hypotheses with some math. If you plug in your function here into function, you plug in 1 into this, you're going to get 0 over 0, like that. Well, that might not mean much. It's really 0 from this side and 0 from the other side, like that. And that would yield positive and negative infinity, sorry. And likewise, it's for 1 from the other side. And you get a similar result, but it's 1 from this side and from the other side, like that. And that again gives negative infinity. And that should be positive, sorry. So you have the first VA is at x equals 1. Let's confirm it for x equals 2. And it's a similar process again. You're left with 1 over 0 from your right side. That gives plus infinity. And similarly, x equals 2 minus f of x is 1 over, like that. That gives negative infinity. And that once again confirms that we do have a vertical asymptote at x equals 2. And those are our vertical asymptotes at x equals 1 and x equals 2. And the horizontal asymptote is a slightly less convoluted to solve for, in the sense that you can just do it as x goes to infinity. And you can also simplify your function like this. And in this case, it goes to 0. And I believe, if my math is not wrong, it's the same for the other side. And so therefore, you have a horizontal asymptote at y equals 0. And yeah, that is that. That is all for today. I believe our next video will be on the introduction to derivatives. And I look forward to that because that's a much more enjoyable topic to make videos on, because there are a lot more interesting problems than just glorified algebra 2 problems. So thank you for watching this video, and bye-bye.